Let us start today's lecture of soil dynamics. In the previous lecture, let us quickly do a recap. We are continuing with our module 4, that is dynamic soil properties. We had learned in the previous lecture, like for determination of the soil properties, similar to the static case, for dynamic case also, it can be classified in two major categories, field test and laboratory test. Within field test, we have sub-classified mainly in two broad categories. One is called direct test, another is indirect test. Within direct test, we have seen seismic reflection test, seismic refraction test, SASW or MASW test, seismic crosshole test, seismic downhole, uphole test, etc. And indirect test are which are common for static test, field test like SPT, CPT, BPT, pressure meter test, dilatometer test, all these are tests for static property determination for the soil, which can be also used for determination of dynamic soil properties using some empirical relations. Then seismic reflection test, we have seen what are the basis of the seismic reflection test. Coming to the next type of test, which is seismic refraction test. These are common geophysical tests you must have studied in your undergraduate soil mechanics course also. So, just to brush up your memories, suppose we have recording equipment here, where the explosive charge at a shallow hole or by using vertical impact or horizontal impact, we are providing the vibration in the soil system, and we are using several receivers which we call as geophones at different distances. Then through refraction, we can find out the travel time versus distance curve for the fast arrivals. And if we have the horizontal layers, this is the source point and various receivers can be here. So, direct waves can reach here directly, whereas the refracted waves can get refracted at the boundary and come back there. So, this is the way the waves can travel at the boundary. They are traveling in this direction and refracted back and going to the receiver. Okay? So, there is a difference between the previous method of reflected test and this is refracted test. So, this is the major difference. So, from the difference of the time, you should identify which one is my reflected wave arrival time, which one is my direct wave arrival time, and which one is my refracted wave arrival time. And using the simple Snell's law for critical angle of incidence and simplifying the different expressions, the thickness of a layer can be obtained. So, if we use multiple number of geophones to receive the data from a particular source and then plot the time versus distance, we will see that after a certain distance, there will be a kink in the graph. So, that point of discontinuity is nothing but showing the changing of a layer. That is, from those layer interfaces, the waves are getting refracted, and slope of each of the linear segments will give us the value of the wave velocity in that particular layer. So, this is the pictorial representation of how from source to the refraction is getting placed between the first layer and second layer boundary, giving us the value of V1, then second one V2, third one V3, next one V4 and so on. There is one assumption that the V1 is less than V2 is less than V3 less than V4. So, if it is not so, our test will give some erroneous results. So, these are the few drawbacks we should remember about this particular test. And also thickness of any kth layer as expressed by US Army Corps of Engineers. This is the expression used to obtain the thickness of any of the layer, kth layer, first layer, second layer. You can use corresponding lower layer velocity and the upper layer velocity to find out the thickness of the upper layer velocity. This is again a representation what I have mentioned just now. Slope of this will give us the velocity in that particular media, velocity of wave in that particular media. Now, what happens if instead of horizontal layers we come across with an inclined layer like this? So, below ground we have an inclined layer, the top layer is like this with thickness of d d here, whereas d u at this place. So, alpha is the inclination of that layer with respect to horizontal. So, what I said, in these type of cases of inclined or irregular layer, you use source at this point and at two other ends you use the geophones or receiver stations. So, arrival time and distance you plot for both the sides of the different geophones from both left hand side of y axis and right hand side of the y axis, and they will meet at some point, and which will help us to obtain the inclination alpha using the relationship obtained for the velocities for two directions or two thickness of the soil from two sides. Now, coming to the spectral analysis of surface wave, which is very commonly used even nowadays also for determination of shear wave velocity of the soil. So, some of the characteristics let me mention first. Spectral analysis of surface wave can be used to obtain the shear wave velocity Vs of the soil. This test is applicable to sands, gravels and soils with fine, that is for most of the types of soil it is applicable, which is a advantage of this test. Now, based on the dispersive property of Rayleigh wave, Rayleigh type surface wave propagating in a layered media, we obtain the Vs. What is the basic physics behind the test? That is, as the name suggests, spectral analysis of surface wave. By using that vibration at a very shallow depth of the soil, what we are creating? We are creating the vibration and waves getting generated, and they are traveling through the media. Now, it can produce both body wave and surface wave. Now, surface wave will arrive obviously first, like a direct wave kind of thing. Now, what are these surface wave? Most of the energy is taken care of by Rayleigh wave, as I have already mentioned in the theory of wave propagation. So, those Rayleigh wave, when it reaches at the receiver stations, so we record the arrival time of those Rayleigh wave and the corresponding distances from that charge point to those receiving stations. Now, this Rayleigh wave will help us finally to obtain the shear wave of the soil. How? Because we know from the relationship between Rayleigh wave and shear wave, depending on the Poisson's ratio of the material, we can compute the shear wave velocity of the material, right. So, that expression is actually used to obtain the shear wave velocity. So, it is kind of we are using first surface wave of Rayleigh wave, then through which we are finally getting the value of shear wave velocity. So, remember this. Now, it measures surface wave velocity at numerous wavelength, produces a dispersion curve which indicates that surface wave velocity is variation at that site. Obviously, depending on your hammering technique at different time, it will create different wavelength of the waves traveling through the media, and you will get a set of curves which will help you to obtain the surface wave velocity or Rayleigh wave velocity. That finally will be used to obtain Vs, and these velocities are representative of material stiffness, because as we know the shear wave velocity actually represent how stiff the material is. If the Vs value is lower than the other material, then it automatically means that the stiffness of that material is lower than the other material, and it can be converted to obtain the small strain shear modulus. What is small strain shear modulus? I will explain these things in subsequent lectures. That is expressed by G max. G is the expression for shear modulus. So, G max is nothing but called maximum shear modulus or small strain shear modulus. So, that G max is given by rho times Vs square. Vs is shear wave velocity of the soil and rho is mass density of the soil material. So, this is the expression used to obtain the shear modulus. Now, these surface waves are generated by applying dynamic vertical load to the ground surface, as we have already seen how the agitation or the vibration is getting created. These tests are non-invasive from surface and can use manual method, that is not necessarily you need to use the hydraulic jack or hydraulic machine to create the vibration. You can use a manual method by using the drop weight or sledgehammer type of method to create the vibration, or a shaker. Shaker is of course a instrumented vibration you are getting created in the soil media, and advantage is of the shaker that frequency of the blows also you can measure. So, you know one more input, whereas in your manual method you cannot find out what is the frequency of the vibration you are getting generated in the test procedure. What are the other major characteristics? For SASW test, we need at least 16 meter of open space in the direction of where from source to receiver is placed. So, otherwise what will happen? The waves will not get sufficient distance to travel to generate as both surface wave and other body waves. So, you cannot differentiate the time arrival and etc. So, we need at least a 16 meter of open space. So, remember this point, because many a times in field you will find that contractors or field engineers, they are not following this criteria. In that case, you are not sure whether you are measuring Rayleigh wave or you are measuring some other wave like even body wave, because the time overlapping may occur. So, that is why be sure to provide a minimum of 16 meter. If you are providing more than 16 meter open space, that is well and good, and it helps you to identify some of the kind of obstructions if they are present, because then changes of wave characteristics will occur, because material changing means the Vs or Rayleigh wave in that particular media will completely change. Instead of soil, if we have say concrete material, some very old pipe or very old piles are already hidden below the soil, which is not known. Say some historical construction was done and then it was damaged and nobody knows that below the ground what exists. Many a times it happens, mainly in the urban areas, that when you are going for a new construction, you will find that when you are doing the SASW test, suddenly at one particular point or one particular layer you are getting very high value of Vs, which is not commensurate with your other recording stations values of Vs for that same region. What does it mean? Definitely at that region you have some very hidden stiff material below the ground, which is creating the recorded value of very high Vs value. So, be aware of these points, that is how to identify the very high value of a Vs or sometimes even very low value of Vs also will help you to identify some sandwich of thin layers. What does it mean? If you have a continuous pretty large thick layer of some stiffness and soon after that below that you have another similar stiff material which is following the criteria which we are mentioning, that the upper layer stiffness is lower than the lower layer stiffness, but in between them suppose if some very small thick material, that is sandwiched material we call, which is very weak in nature because of geological formation of the soil, some sandwich layer or hidden layer lies between these two major layers. What will happen? Suddenly you will see that there is a jump or means jumping down the values of Vs at some interfaces or at some recording stations. That will indicate the presence of a very soft layer or sandwich layer. And many a times if the sandwich layer thickness is pretty small compared to your major layer for which you are obtaining the Vs value, you may not even identify that change in Vs value. You may sometimes ignore also, because the changing of the values in that two layers will be so sudden and time arrival and things like that will be so abrupt, you will not able to find out. And what are the other major characteristics? They can test up to a depth of about 20 to 30 meter. That is, it can identify the properties of a soil of thickness of about up to 30 meter depth. Beyond that, it requires more open space, as it is mentioned. So, as more deeper strata you want to identify their dynamic shear wave velocity value, you need a more open space to conduct this test. And as I have mentioned, MASW test is also the similar test, only thing you use multi-channel, multi-sources and multi-receivers. Okay. So, this is the pictorial representation or configuration of a SASW test. We have a source, different receivers at different distances. Suppose distance D1 at first receiver, D2 for the second receiver, and receiver spacing is changed in such a way that this summation of D1 plus D2 they remains constant, and travel time between receivers calculated for each of the frequency in this way. So, this is the phase difference function and this is the frequency, this is the travel time, and the distance between the two receivers, that delta D, which is nothing but that D2 minus D1, that is known to us, because that is how we have kept on our ground surface the receivers. Then the velocity and wavelength, they can be computed. So, this is the typical way how the phase velocity and wavelength they are plotted. So, this is after these researchers typical experimental curve, you can plot it like this, which will give you the value of VR and lambda r. These are nothing but your Rayleigh wave velocity, okay, from which now you have to use the relationship between Rayleigh wave and shear wave velocity, and you will get the expression for Vs. Now, after obtaining the value of Vs through this SASW test, we need to do some correction of the raw measured value of the Vs. So, raw data of Vs measured at the site needs some correction. That major correction is known as overburden stress correction. Why this correction is necessary? Because as you know, if we go deeper and deeper in a soil media, even though it is a homogeneous or same media, if we continuously move down from the ground surface, what will happen? Because of the overburden stress, the stiffness will keep on increasing, right. So, obviously, your recorded Vs value as you go deeper and deeper will be higher and higher, but that is not the basic property of that soil media. It is just because of the overburden, clear. So, we need to do the overburden stress correction factor, we need to apply to this recorded Vs data, so that the effect of this depth or effect of overburden is not present in our reported soil data. How we do that? To do that, we need to identify a reference value, that is with respect to what stress condition, what overburden stress condition we can say that okay, this is our standard value of Vs. So, that referencing of the overburden stress is used here. Let us look at the slide here. So, that reference value of the pressure or the overburden stress is nothing but 1 atmospheric pressure, which is equal to about 96 point something kPa, which for all practical purposes we take approximately equal to 100 kPa. So, 100 kPa is the standardized or reference value of overburden stress, which will give us the correct Vs value. That is, with respect to that standard value of Vs, standard value of overburden stress, we report our Vs value. Because otherwise, as we go deeper and deeper, Vs value for the same soil will keep on increasing. That will not give us the correct idea of what is the exact Vs value for the soil we should use in our design. So, to avoid that, we are doing this referencing at a particular pressure or at a particular stress, which is the 1 atmospheric pressure. And this is the formula used for applying the overburden stress correction factor. This Vs is the field recorded data, raw data value which we have recorded from SASW test. Pa is 1 atmospheric pressure or 100 kPa. Sigma V naught dash is nothing but effective vertical stress at the point where you are measuring this Vs. So, suppose your raw Vs data you have measured at 25 meter depth below the ground, then the effective vertical stress at that 25 meter below the ground you need to compute, and the unit of that must be kPa if you use the unit for Pa as 100 kPa. So, remember that, do not forget that if you use this as 1, that is 1 atmospheric pressure, then convert the unit of effective vertical stress also to atmospheric pressure unit. That is, unit of them must be same, so that the dimensional things are maintained. That is, whatever the unit of this raw Vs in meter per second you have recorded, the same unit will carry forward to your corrected value of shear wave velocity. To the power 0.25, this coefficient is used to apply the correction or to apply the reference standardization, and that is how the correct value of Vs is calculated from this test. Now, when we are studying any test, we must know what is the major drawback of the test, because the major limitation of any particular test, unless we know, we will blindly follow the results. So, that is why it is very important, along with the characteristics of test methodologies and values, we must know the limitation of the test, which will help us to put our proper engineering judgment for a kind of values which we are getting recorded. So, let us look at it. What are the major drawbacks? In this test, no sample is obtained for soil classification, because as the test methodology we have described, there is no scope that we can get a soil sample for this test. So, to avoid this limitation or to avoid this drawback, what one should do when we are doing the field test? Simultaneously, we should take out some sample from some borehole to cross check whether yes, the same soil material is existing at that particular layer where we have obtained the SASW, that Vs value, or not. If it is not the same soil layer, then obviously we can suspect some drastic change in the Vs value recorded. So, this is kind of a cross verification. Now, the second point is thin layers may be missed. What I have told just few minutes back, if there is a sandwich layer between two major layers, that thin layer may be missed and we may not get a Vs value for that thin layer. But remember, in case of damages due to dynamic load, for example, say due to earthquake load, may occur because of the presence of this thin layer, which we are not able to identify in this test. So, how to overcome this drawback? Once again, this taking a sample is a good option to identify if really there is some thin layer or not. Third limitation of this test is, suppose we are getting continuous increase or sudden increase in Vs value from our record of this SASW test. It need not necessarily mean that it is providing us a very stiff or good soil material, which in turns mean that their liquefaction resistance. We will discuss this soon in the course of our study, what are liquefactions and how they are related to Vs and so on. So, at this point just note it down that increase in the shear wave velocity need not necessarily be due to the original soil property or the stiffness of the soil. It may be due to some cementation effect, external cementation effect. What is that? As I have mentioned, presence of some buried structure in the long back or in history, which we are not able to identify or which we do not know. Long back, suppose some buried structure where there are some buried pipeline, buried utility lines, buried concrete piles, which are not in use and on ground surface, which are not visible also. So, sudden rise in Vs value should not give you an idea that, oh, I got a very nice or very stiff soil layer and easily we can put and easily we can recommend that this soil is not going to liquefy. It may not be so. That sudden rise in Vs value may be because of this some cementation effect due to the external material, presence of external material, not because of the parent soil material. So, remember these major drawbacks, and then whenever you are using the value of Vs for further interpretation of design or construction, you have to be very careful. Some other types of direct test for determination of dynamic soil properties are seismic cross hole test. So, seismic cross hole test, this is the schematic diagram, how the direct measurement using two, these are nothing but cross holes are nothing but similar to you create a borehole, and within the borehole you apply your source, that is create the vibration, and in another borehole adjacent to it you put your receiver and record that travel of the waves. So, that is the direct measurement using two borehole configuration, and instead of two borehole you can utilize multiple boreholes also, interval measurement using the 3 borehole configuration. So, these are referred to as seismic cross hole test. Here also the same principle of traveling the waves, the direct wave, reflected wave, etc., can be adopted, because there will be clear time gap between the waves arriving at the receiver point. And also this is a quite useful test, because whenever you go for field investigation or site investigation, many a times we have to do or we must do the borehole. So, after doing the static test, when the boreholes are free, you can utilize them for your dynamic test also by using this cross hole test. Another type of common test is seismic downhole test or seismic uphole test. So, what is uphole test? Look at figure A. When in that borehole, if you put the source of vibration inside the borehole and keep your receiver on the ground surface, that is called uphole test. And if it is the positions of source and receivers are vice versa, that is look at figure B. In that case, source is located, that is where the vibration is created, that is located on the ground surface, whereas your recording station or receiver point is located inside the borehole, then it is called seismic downhole test. And then all the methodology are like similar to the travel time method. Now, coming to another major category of test, which are laboratory test for determination of dynamic soil properties. So, common laboratory test for determination of dynamic soil properties, some of them can be classified in 3 major subcategories. One is sample test at low strain condition, that is you apply your cyclic or dynamic strain at low strain level, you conduct the test and you measure the strength of the soil. So, within that category we have tests like resonant column test, piezoelectric bender element test, So, these are sample test at low strain level. Then another category can be sample test at high strain level, and within that sub classification we have different tests like cyclic triaxial test, cyclic simple shear test, cyclic torsional shear test, etc. And another category is model test. In model test, the sub classification we can have shaking table test or shake table test and dynamic centrifuge model test. So, these are the common model test can be used to obtain the dynamic soil properties. Now, coming to a small description of each of these tests. In the sample test where we are using the concept of small strain level test, there the first one is resonant column test. So, this is the pictorial representation of the apparatus which are used: accelerometer, counterweight, supporting ring, drive coil, a magnet. These are the accelerometers here. So, this is the top view of the loading system, and this is the cross sectional profile. You can see LVDT, proximeter probe, proximeter holder. This is the top cap, then your soil sample or soil specimen, then fluid path, supporting ring, drive coil, and here you provide the accelerometer. Okay. So, the boundary condition for this resonant column test, you can provide different boundary conditions. It can be fixed end here, free end here, fixed free. You can provide fixed fixed. Depending on the boundary conditions of your soil specimen, you need to use different equations to obtain the shear wave velocity from this test. So, from this test we can obtain the shear wave velocity from the length of the soil sample and from the resonant frequency. As the name suggests, resonant column test, what we apply different frequency of vibrations through this sample, and we want it to resonate. So, you plot that forced vibration of dynamic displacement versus different frequency input. You remember that half power bandwidth method we have seen. So, the same concept is used here in resonant column test. You can resonate the soil specimen at, you apply different frequency, find out the resonant frequency and use that to obtain your shear wave velocity expression based on the boundary condition. Boundary condition is very important, whether it is fixed fixed or fixed free. Depending on that, the fixity length of your soil column depends on. Coming to the another type of small strain level sample test is piezoelectric bender element test. Piezoelectric bender element test, in this case, this is the direction of shear wave propagation, one bearing plate here, and if it is a 0 voltage, then it will be standing like this. If you change and apply voltage, that is from positive to negative, due to the propagation of the wave through the sample, it will bend in this. So, like this, using the bender element, the direction of the element tip and soil particle moves in this perpendicular direction to the direction of shear wave propagation. So, this way also it can give us the value of shear wave velocity, and remember this is again at the small strain level. So, I will come in the application of these measurements for liquefaction and other studies of dynamic soil properties. In those cases, I will mention the advantage and disadvantages of this test. Coming to large strain dynamic test for soil, cyclic triaxial test. So, this is a typical triaxial test apparatus which all of you know. We apply cell pressure, this is O-ring, rubber membrane, here we have the soil specimen, cell wall, this is the load cell and then LVDT. What is the major difference from the standard static triaxial test and cyclic triaxial test? The major difference is the deviatric stress what we will apply in static case, that is in one direction only of course, but in cyclic test it will be cyclic in nature like this. So, that is the major difference from a static triaxial test to cyclic triaxial test. And obviously, with respect to time, you should record this application of your deviatric stress to the soil sample, and then you can get the development of pore pressures and so on. So, a kind of representation of the deviatric stress with respect to time, which where you are applying the cyclic load, can follow this kind of pattern. Suppose if you are providing some harmonic load in the cyclic load, so this is the typical pattern how you can provide. So, what it says, time histories of deviator stress, and these are corresponding stress path. So, these are the input deviator stress and these are the stress path in the QP plot. Okay. So, the first one, this A, it shows the test for isotropically consolidated condition. The second one shows anisotropically consolidated conditions with cyclic deviator stress amplitude greater than deviator stress during the consolidation, producing a stress reversal. So, that is why this case, this applied deviatric stress is not with respect to your 0 line, but it is with respect to some other positive line about this axis. Why? Because here after applying the deviatric stress for your consolidation, then you are applying additional cyclic deviatric stress. So, that is why it automatically gives you the representation of the deviatric stress with respect to time like this, and the corresponding stress path will be like this. And the third one, the case C, shows the case of anisotropically consolidated conditions with cyclic deviator stress amplitude less than deviator stress during consolidation, but there is no stress reversal. There is no stress reversal, that is why the entire thing is in this one side of the axis and corresponding stress path here. I assume, though this is not within the scope of this course, you understand what is meant by isotropically consolidated test for a triaxial under static condition, what is anisotropically consolidated, and for static triaxial test we have three categories we know: UU test, CU test and CD test. Now, within CU test and CD test we can have again two more sub classification. I assume that all of you are aware of it. Those two sub classifications are isotropically consolidated undrained, that is ICU test. Another is called anisotropically consolidated undrained, so ACU test. Again, CD test can be sub classified as isotropically consolidated drain test, and another sub classification will be anisotropically consolidated ACD test. So, what are the major differences? Let me just give you the major principle or background of the study. When we are doing the consolidation, the first term is showing the consolidation, as you know in the triaxial test, whether you have consolidated the material and then applying the deviatric stress or not. So, during the consolidation process, isotropic means you apply a cell pressure uniformly from all the directions. What is anisotropic then? Anisotropic means in any particular direction you provide a larger or smaller cell pressure. How you can generate that? So, in one particular direction in your soil sample, you provide another element, that is another weight, through using a kind of balance. You provide another extra load in the soil sample in horizontal direction by providing an anisotropy in a particular direction. That will give you the anisotropic condition when you are doing the consolidation. So, those cases will arise or will give us the condition of anisotropically consolidated undrained test and anisotropically consolidated drain test. These tests are not so common, but in the case of dynamic soil test, we should do this kind of test also, that is anisotropic cyclic triaxial test. Because unless we do the anisotropic test in one particular direction due to the anisotropy or the changes in the stresses or property, we are not able to identify how the behavior of soil sample is going to happen, because it is not necessary that earthquake or any dynamic load when it is arising, it will uniformly act around the periphery of your soil sample. It can be in any particular direction. So, that may create the condition of anisotropy. So, remember these things, it is not so common in your static test, but in dynamic or cyclic triaxial test, anisotropic test should be conducted. Now, coming to another type of large strain test, cyclic simple shear test. In this case, the same direct shear test in static case, whatever we use, the same concept and same apparatus is used. The major difference is this one. When we apply the shearing load in the static case for a constant value of normal load, we apply it in one direction only. So, that the soil plate that gets sheared, right, the soil sample for under a constant normal load. In this case, under that same constant normal load, we apply a cyclic horizontal load or cyclic shearing load. So, that is the major difference between a static simple shear test and cyclic simple shear test. Then another type of large strain test is cyclic torsional shear test. What we do in this case, suppose if we have a annular cylindrical or hollow cylindrical apparatus like this. So, we apply the axial stresses, provide a torque in the soil specimen, then internal pressure and external pressure that get generated within the soil sample and torque is applied. So, these are the stress conditions from which we can find out the dynamic soil properties. So, these tests, whatever the shear versus normal stress or shear stress versus shear strain profile, what we are getting from these tests, we will see soon in our lecture. Coming to another major category of test in laboratory are model test. Now, within model test, as I have already mentioned, two commonly used model tests are shake table test and dynamic centrifuge test. So, let us look at here shaking table test. This is a typical diagram of a shaking table test. It is nothing but, as the name suggests, we have a table, on top of it you have a peripheral boundary, instrumented wall, or whatever test you are going to do, depending on that you create this boundary at different distances. And suppose this picture is showing for a dynamic earth pressure computation test. So, there will be a retaining wall, you filled up soil at one side, another side there will be a dredge level of the soil, you instrument that wall, and what you do, you then start shaking this table. So, as the name suggests, there will be actuator, it will be coupled to this, it will start shaking this table. And of course, this shaking table test can be of different directional, that is one directional shake table test. Suppose if you have the actuator only in this direction, then you are creating the shaking or vibration in this one direction only. If you are able to create in this direction also along with this, if you have an actuator in this direction as well, you have bi-directional shaking table test. If you have another one to give the vertical one, then you have 3-directional shaking table test. Now, if you have the actuator to provide a rotational shaking also to your table, in that case you can get torsional or rotational directional degrees of freedom also. So, the best shaking table test will be of that 3-dimensional in 6 degrees of freedom, right. That is, all 3 linear shaking you can provide, that is 2 horizontal and 1 vertical, and all 3 rotational shaking also you can provide. So, now in India we have several such advanced or very high equipped shaking table test. For example, one at CPRI Bangalore, that is Central Power Research Institute. These are all under CSIR labs, all are research institute. That CPRI Bangalore is having 6 degrees of freedom, that what I have mentioned, 3 horizontal and 3 rotational vibration you can create in that. That type of shake table is available, one can do experiment in that. The other one is at ACRC Chennai. So, ACRC Chennai along with collaboration with BARC, they also got a 6-directional. They actually got 2 such shaking table tests, one a big size, another is small size. With collaboration with BARC Mumbai, they have created this testing facility. Other than that, from several years there are several shaking table tests available in various research institute as well as academic institute, like IIT Roorkee is also having shaking table test, IISc Bangalore is also having shaking table test, but those are limited to only either unidirectional shaking, horizontal only, or bidirectional at most shaking. So, other directions are not available. Now, another model test is centrifuge test for obtaining the dynamic soil properties. So, in centrifuge test, this is the cross section of a typical geotechnical centrifuge. We have a bearing, slip rings, we have a basket, test basket, here counterweights are provided. About this point, this keeps on rotating and the centrifugal force is getting generated, and that is how the principle is used to scale up the model dimension which we use in our geotechnical engineering to a prototype or actual field dimensions. So, you remember, or those of you who are aware of the centrifuge testing facility, they know the drawbacks of 1 gravity 1G test, model test for our geotechnical engineering problems. Why? Because in structural engineering it is pretty common to do 1 gravity or 1G model test, that is, you scale down your 10-storied actual building to a small model 10-storied building and do the test. You will get fairly accurate values of stresses, displacement and so on from the model test. You apply the scaling laws, etc. Whereas, if you apply to do the same thing for geotechnical problems, that is where you are handling with soil samples or problems where suppose you have a soil slope or earthen dam, what happens? The concept of that scaling down from the actual prototype or field problem to a small model dimension is not giving you always the correct value of the stresses and displacement getting generated in model to prototype. Why? Because in this case the scaling laws are not that simple, not that linear scaling laws. In this case, many a times we have the concept of pressure bulb generated in case of suppose we want to find out the bearing capacity or settlement of footings. So, if we do the test of a actual foundation, say a raft foundation of 10 meter by 15 meter of raft size, that if you scale down in the model say 1 meter by 1.5 meter to maintain the ratio and do the test with the soil media, also you have changed. Suppose in actual case we have below, just below the raft about 20 meter depth one particular soil, then below that another 10 meter depth of another particular soil, and if you scale it down with respect to prototype to model, what you will do? You will put the 2 meter depth of that particular soil below the footing, then again another 1 meter of next layer of soil. But when you are doing the test, doing the bearing capacity failure test or finding out the settlement of the footing under some particular load, your pressure bulbs getting generated in this small 1 gravity 1G test in laboratory for the model test. The pressure bulb, it may go through the other layers also in model test, whereas it may need not be necessary for your actual prototype case, where you are getting sufficient 20 meter depth. So, these are the major cases. Also, suppose if you want to test a pile, now scaling down a big actual pile say of 20 meter length in prototype, you are scaling it down in the laboratory say to 1 meter depth and doing the test in a soil profile. Again, the same theory of scaling laws are not accurately used for geotechnical problems, because for piles also the zone of influence will come into picture, which will not be commensurate with your model and prototype. So, these are the basic disadvantages of using one gravity model test in geotechnical problems compared to other areas like structural engineering or other areas. So, that is why using this shaking table test for a dynamic soil properties or the behavior of dynamic say earth pressure or dynamic bearing capacities, things like that are not always correct or are not always giving us the true result. So, we have to be very careful to understand what are the limitations of the shaking table test for geotechnical engineering problems. Though people worldwide they use it, but it is not giving us accurate result. And when we will get more accurate, obviously as bigger the size as we can use. So, if we can use actual prototype sizes for our testing in shaking table test, then obviously yes, it will give you the correct result. So, to avoid that kind of scaling effect for the geotechnical problem, the best solution is to apply the geotechnical centrifuge facility, where the stress conditions are first maintained, then all other dimensions are getting obtained, so that your small model can be scaled up to your actual prototype by using at high gravity level. So, it is something like you are doing the testing of your material in some other planet, where you have say high value of G level. So, with this we have come to the end of today's lecture. We will continue our lecture in the next class.